Almost 12 years ago, in March 2024, Java 8 was released, and with it, the Stream API. At the time, it was a fundamentally new tool for processing data streams. I'd like to start with a quick refresher on the Stream API. A stream pipeline starts with a source which creates a stream from a data structure, for example, the stream method of a collection. Then we have optionally intermediate operations that transform the stream and its elements, such as filter, limit, map. And finally, we have a terminal operation which collects the elements of the stream, for example, with toList into a list. Now let's take a look at a concrete example. We have a list of words here, which we turn into a stream. When the stream method is called, a so-called splitterator is created internally. A splitterator is something like an iterator, but a splitterator can split itself into two parts, and those can split again, so that the data can then be processed in parallel in a parallel stream. In addition, a splitterator has so-called characteristics. These are properties of the data source that can be used to optimize the stream processing. What that means, I'll show you later in an example. Then we say filter, we want words that are at least 8 characters long. Then we say limit 3, we want at most 3 results. And finally comes the terminal operation toList, and only its invocation actually starts the processing. And it proceeds as follows. This is meant to represent the stream pipeline, and this is the list of elements. The splitterator now pushes the first element, avocado, to the filter stage. That stage checks whether the word has at least 8 characters. It does not, therefore the filter operation does not pass the element on to the next stage of the pipeline. The splitterator pushes the next element, banana, to the filter. That one is also too short and is not passed along. Then comes the third element, cantaloupe. Here the filter predicate evaluates to true, so the filter passes the element on to the next stage of the pipeline, the limit operation. That stage has an internal counter which starts at 0, and therefore the limit operation knows it hasn't passed any elements on yet. It pushes the cantaloupe to the next stage and increments the counter by 1. The terminal operation toList collects the element into a list. Just like the cantaloupe, the dragon fruit now also passes through the pipeline. The counter of the limit stage is now at 2. The fig is not passed on by the filter, and the grapefruit once again goes through the entire pipeline, and the limit counter is now at 3. What does not happen now is that the next element is sent into the pipeline and rejected by the limit operation. Instead, after passing along the third element, the limit operation sends a signal back to the source indicating that no further elements are needed. And as a result, the remaining elements are not sent into the pipeline at all. And now we come to the main topic of the talk. Here's the stream pipeline from the beginning again. And these intermediate operations are quite limited in terms of selection. The Stream API contains exactly 11 intermediate operations: filter, limit, and map, flat map, map multi, which is a faster flat map, distinct sorted, skip, take while, drop while, and peek. And if you look at the feature requests from the Java community, you'll find many wishes for other operations, especially ones like window or fold. But instead of integrating all these requested intermediate operations directly into the stream interface, the JDK developers decided to take a different approach. They developed an API that allows, on the one hand, us Java developers to implement any intermediate operation we want ourselves, and on the other hand, the JDK developers to implement the most requested operations and make them available with the JDK. And this new API is called Stream Gatherers. Stream Gatherers were introduced as a preview feature through JDK enhancement proposal 461 in Java 22 in March last year, exactly 10 years after the introduction of the Stream API. They were reintroduced with JEP 473 in Java 23 and finalized in JEP 485 in Java 24. And now I'll first show you how to use predefined gatherers and afterwards how you can implement your own. In the first demo, we have this list of words and we want to group them into sublists of 3 words each. This is also known as a window operation. I have prepared the word list and we'll turn it into a stream. And now, instead of saying, for example, window fixed 3, which would require a change to the stream interface, we can say gatherers window fixed 3, and then collect that into a list and print it out. And here we can see the 3 sublists. Besides window fixed, there's also a predefined gatherer windows sliding. And that creates sublists of 3 elements, each shifted 1 position to the right. And this pattern, gatherers, might look familiar to you. ToList only exists since Java 16. What we had to write before was collectors to list, or to unmodifiable list to create an unmodifiable list, just like ToList does. And now you can clearly see a gatherer is to intermediate operations what a collector is to terminal operations. This way, JDK developers can gradually add more intermediate operations via the gatherers class without having to modify the stream interface every time. And just as we have always been able to write our own collectors for terminal operations, we can now also write our own gatherers for intermediate operations. A stream gatherer consists of 4 components, of which 3 are optional. The mandatory component is the integrator, and that's where we'll start. The integrator is the central component of an intermediate operation that receives an element from the previous stage of the stream pipeline, optionally transforms the element, and then passes 0, 1 or more elements to the next stage of the stream pipeline. And it may also terminate the stream early, as the limit operation does, for example. I'd like to show you how we can develop a gatherer using only such an integrator with 2 examples. One that implements a map operation and one that implements a filter. Integrator is a functional interface with an integrate method. This method receives 3 parameters, a state of type A, which we don't use in the first 2 examples, so you can ignore it for now. The element of type T, this is the element that the previous stage of the pipeline sends to this stage, and a downstream through which we send elements of type R to the next stage of the pipeline. Downstream itself is also a functional interface with a push method. We pass the element to it and it returns a boolean indicating whether downstream wants to receive more elements. If there's, for example, a limit operation downstream, this would return false once the limit has been reached. Back to the integrate method. This one also returns a boolean, which indicates to the previous stage of the stream pipeline whether we want to continue processing more elements. If not, we return false, which effectively sends the stop signal that I showed you earlier in the animation. And now we want to write such an integrator for the map operation. First, we need a mapping function. And let's say we'll map a string to its length. And the integrator now has the types void, that is the state that we'll ignore for now, string for incoming elements, and integer for outgoing elements. We implement the integrator as a lambda that takes the state, the element, and the downstream. Inside the lambda, that's in the integrate method, we apply the mapping function to the element, which gives us the mapped element. And then we send the mapped element to the downstream. And as you remember, push returns a Boolean indicating whether more elements should be sent, and we forward that value unchanged to the previous stage of the pipeline. This integrator can only return false if the downstream does so. On its own, it would never stop requesting more elements. That's why such an integrator is called greedy. And if we indicate that to the stream pipeline, it can optimize the evaluation for early termination. We do that by wrapping the integrator with integrator of greedy. To finally create a gatherer from this integrator, we use the static method gatherer of integrator. And now we can use this gatherer in a stream pipeline. Up here we have our words list again, and now we say words stream gatherer to list, and I'll print it out. And here we see the length of the individual strings. And now we can extract this code into a method named mapping. We can inline the gatherer and the mapping function. And this looks quite elegant now. And here below we have the code for this simple mapping gatherer with just an integrator that maps the element and pushes it into the downstream. We can inline the return value here, and the unused state variable can be replaced with an underscore since Java 22. And if we now make this method generic and replace string with T and integer with R, then we could here use, for example, to uppercase, and we would get a string list then. And if we run the program again, we see the elements mapped to uppercase. With this mapping gatherer, we have implemented exactly the same operation as the map operation of the stream interface. And by the way, you can find this project on my GitHub account. There will be a QR code at the end of the presentation for that. Next, I would have liked to show you how to implement the filter operation using a stream gatherer, but unfortunately, we don't have enough time for that. You can take a look at it later here at Integrator Demo Complete Filtering. Back to the slides. That was the integrator, and that was also the most important central component of a gatherer. The other components are used for stateful and parallel gatherers. In the next demo, I'll show you how to create the limit operation that was part of this animation, and it had a counter here to terminate the stream early once the desired number of elements was reached. And it's exactly for this counter that we need the state variable. The one I've been skipping over in the code so far because the map and filter operations don't need any state. But now for the limit operation, we do. And the state first needs to be initialized, and we do that in the initializer. And I'll show you how to do that in the IDE. The initializer is a supplier that creates an object to hold the state. For counting, for example, an atomic integer works well. And the initializer creates this state object with atomic integer new. Then we write another integrator, and the state type is now atomic integer. For the element type, we'll start using string, which we can later parameterize again. And the downstream type is the same as the element type because the limit operation passes the elements unchanged to the next pipeline stage. We write the integrator again as a lambda. And now we say, as long as the state, the element counter, is less than, here we need a variable, max size. I'll set it to 3 and move it up here. So as long as the counter is less than 3, we push the element into the downstream. Then we increment the counter by 1. And we also need to remember the downstream's return value and return it. And otherwise, if we have reached the limit, we return false, which will terminate the stream. So this integrator can return false by itself, and that's why we must not wrap it with integrator of greedy. Then we create a gatherer, and this time we need to use gatherer of sequential. In the previous demos, we didn't have any state, meaning those gatherers could also have been used in parallel. Now, however, we do have state, so we can only use this gatherer sequentially for now. Later, I'll show you how to parallelize a stateful gatherer as well. And this of sequential ensures that the gather stage of the pipeline is executed sequentially, even if the rest of the pipeline runs in parallel. And here we pass the initializer and the integrator. And now we say again words. Sorry, this must go down here. We say again words stream, gather, gatherer, to list, and we'll print it out. And here we see the first 3 words of the list. And again, we can extract this part into a method limiting and inline max size and inline the gatherer, and we end up with 3 elegant lines of code again. And with this limiting gatherer, we have implemented exactly the same operation as the limit function of the stream interface. And down here, we could again introduce a type parameter, but I'll skip that for time reasons. Here, of course, we can inline the return value. And here, instead of calling get and then increment, we can just say get and increment. Then we don't need a separate increment, and we can inline the result here. When we later write stateful gatherers that also work in parallel, it's important to know that each thread has its own state. That means that the integrate method is never called from multiple threads at this, with the same state object, at least not at the same time. Which in turn means that the thread safety guaranteed by the atomic integer here is an unnecessary overhead. We can avoid that by using a non-thread safe counter instead. For example, we could introduce a local counter class here with just a count variable. And then down below, use counter instead of atomic integer. Another option would be to use a non-denotable type, but again, we don't have enough time to cover that today. You can check it out later in the repository. Back to the slides. That was the initializer. Unfortunately, we also don't have enough time to look at the two remaining components. There's also the finisher. We need that when we want to push additional elements downstream after all elements have been processed. You need it, for example, in the window operation. I'll skip that for now. And there's also the combiner. We need it if we want a gatherer with state to work in parallel. We'll skip the parallel stream as well. For both components, you can find examples in the repository in the Demo 4 and Demo 5 packages. So with these 4 components, you can now implement any imaginable intermediate operation. Of course, you don't always need to write your own gatherer because for commonly used intermediate operations, the JDK developers have already done that for us. Specifically, there are the following. Window fixed, we've covered that in depth today. Window sliding, I also showed you this one at the beginning. Fold, scan, and map concurrent. We don't have time to look at them in detail. Feel free to check the documentation. There are also open source libraries. You'll find links to them at the end of the presentation. We also have to skip the topic of performance and limitations due to time constraints. Maybe we can still talk about it in the Q&A. And with that, we've reached the end. Behind the QR code, you'll find all the promised links. And if you're interested in more content from me, usually about new Java features, feel free to check out happycoders.eu or one of the other channels. Thank you very much for your attention, and I wish you a great conference day with many more exciting talks.